Okay, I wanted to do something really different today. I wanted to go over something that came out of a video I did recently. It was an integral. Let me show you this now. So a little while back we had this integral, and in the video, and I'll provide a link to the video, we came up with this solution here on the left. But I also mentioned there's another solution that, I don't know, there could be many. And in the video I briefly mentioned that if we used a different method, we'd get a solution like this one on the right. And just notice this is the same as this if we get a common denominator here. So basically the question in the comments from DHY was, how do we know that these two answers are equivalent? How can we show that these are equivalent? What I'm going to do is start with this left answer and show that it's the same as this. You could do it in the opposite direction. I'm going to do it in this direction. So in order to show this, to start with, what I'm going to need is this formula right here. And you may be wondering, well, where did this come from? So I think before we actually use this formula, let's actually just show why this is true. What we're going to do is we're going to start with an integral, a very common integral, just 1 plus dx over 1 plus x squared. And this should be pretty familiar as arctan plus c. And I'm going to assume that we know that this is the value of this integral. We're not going to do the trig sub. And what I'm going to want to do is manipulate this x squared term. What I'm going to do is, let's just look at, if we have ix squared, if we use that, well, we're going to have I squared times x squared, but I squared is just minus 1, so we're going to have minus x squared. So if I want to use ix squared here, I can do that, but I don't want to change it with the negative sign. So what I'll do is, instead of using a plus, we'll just change this to a minus and write this as ix squared. And noticing that is going to be with the minus sign times that minus sign. We haven't changed the value. Then from here, what I'm going to do is just going to do a u substitution to simplify this a little bit. So we're going to call our u ix, and we'll take our derivative du, and we're just going to have I dx. Then solving for dx, that's just going to be du over I. So when I make my substitution here, I'm going to bring the 1 over I out front. Okay, and we're going to have our du in the numerator, and this is just going to be 1 minus u squared. With the difference of two squares, we'll write this as 1 plus u, 1 minus u here. And then I'll just do the partial fractions on this, but very quick. I'm going to move pretty quick because there's a lot to do, and I don't want this video to take forever, so I'm going to keep it moving. So we're going to have a. Now here with our partial fractions set up, okay, what we're going to do, I'm going to use the cover-up method really quick. Now we just notice we can plug a minus 1 in here and get a 0. We cover that up. We plug the minus 1 in here. 1 minus minus 1 is 2. So 1 over 2. This value is going to be 1/2. Again, we'll do the same thing over here. We'll plug a 1 in here. That's when you plug a 1 in there, it's a 0. We'll cover that up, add the 1 in here. Okay, 1 plus 1, 2. 1 over 2. Our b value is 1/2. Now again, I'm going to do this integral really quick. We're going to bring our 1/2, because we have a half in both terms, so we'll bring a half out front. So I'm going to write this as 1 over 2i. And then we're going to, for this integral, we're going to have natural log of 1 plus u. I'm going to leave off the absolute value because our u value is complex. So the absolute value doesn't really have any meaning in that case. And then here, for this other one, we're going to have, again, natural log 1 minus u. But because there's a minus sign, if we were to actually do out the substitution, we have to pull a minus sign out front here. Then the property of logarithms here with the minus sign, that's going to be a division if we put these two together. So we're going to have 1 plus, but I'm going to just do my back substitution. We know u is just ix. So we're going to have 1 plus ix, 1 minus ix. You may notice we're getting pretty close to the goal up here of what we want. But you notice we get this I in the denominator. In general, we don't like I in the denominator. So what we'll do is we'll multiply I times I over I. So that's just multiplying by 1. Well, this will be I squared, which is going to create a minus sign here. Now rewriting this, we're going to write this as 1/2 I. I'm going to take this minus sign, bring it into the power here, and use to flip this so that we get 1/2 I natural log 1 minus ix over 1 plus ix. And you notice that matches exactly. Now the one question you might have, okay, what about this plus c, right? So I should have this plus c here. Up here I'm saying they're equal. I don't have a plus c here, but I have a plus c here. Well, what you could do is you could plug in an easy value, if you plugged in 0. If we're equating this, if we're equating arctan plus c here, I don't know, these can be different c values, right? If you plug a 0 in here, this is 0. If you plug a 0 in here, the x terms go away, you have natural log of 1, that's 0. What that tells us, if it's 0, if we have 0 plus c1 equals 0 plus c2, then c1 equals c2, then essentially you could like do a quick subtract off the c. So just with a quick check like that, that's how you can get rid of the constants in this term here, in this equation here. Okay, so now that we've established this formula, let's go on to use this to show that this left side equals this right side. Now just to save myself a little time, I'm gonna actually call this A and this B, so I don't have to keep rewriting it. Okay, so let's just make a little note here that A equals 2x plus square root of 3, B equals 2x minus square root of 3. And what I'm gonna do is just apply this formula on our equation on the right here. Okay, so now on each of these arctan formulas, I've just made this substitution with this formula. And again, we have A and B in here instead of the actual expression. And so of course we know in our goal, we want just one tan expression. So let's combine these terms using the log properties. And what I'll do is I'll factor out a half I, because we have that in both these. Then we're gonna have natural log, and then we're gonna be, because there's an addition between them, we can actually multiply these together. So from here, what I need to do is just multiply this stuff out. I don't want to keep writing all this other stuff, so I'm just going to focus on what's inside here and multiplying this out. So I'm just going to distribute right over here. So we're going to have 1 minus IA minus IB plus I squared AB. And something very similar here in the denominator, we're going to have 1 plus IA plus IB plus I squared AB. And then continuing with this, what I'll do, rewriting it, I'm going to factor out, and for these middle terms, I'm just going to factor out a minus I, and so we're going to have an A plus B here. Okay, and very similar in the denominator, we're going to have 1, we'll factor out a plus I, and we'll have A plus B. Then here, I squared again is minus, is negative 1, so we're going to have minus AB minus AB. And then at this point, I'm ready to use my A and B, so like if we come back here, we have, again, here's our A and B. Okay, so A plus B is just 4x. Noticing when we add those, the square root of 3's cancel. And then A times B, because it's a difference of squares, it's going to be 4x squared minus 3. So plugging these x values back in, we're going to have 1 minus, let's see, we're going to have a 4x minus, and then this thing, we're going to have minus 4x squared plus 3. The denominator, we'll have 1 plus I, 4x, and then we'll have the exact same thing here, minus 4x squared plus 3. Then just to save myself a step, I'm going to add this 3 to the 1 and get a 4. Okay, we'll have a 4 here, and the same thing here. We'll rewrite this as a 4. So because we have a 4 and everything, we could essentially like factor out a 4 and then the 4's would cancel, but I'm just going to like do it quick like this. We're just going to cancel all these 4's, and these are going to become 1's here. And then I'm just going to rearrange this. I'm going to bring my 1 and my minus x squared together. So we're going to have like 1 minus x squared minus ix. So, and then down here, we'll have basically the same thing, kind of, but we're going to have a plus ix there. Then from here, I'm going to real quick multiply top and bottom by minus 1. So I'm actually just multiplying by 1. But it's just going to, I don't know why I'm doing this. It's just going to make it a little simpler for me to explain. So when I do that, we're going to have x squared minus 1. We'll change the sign up here. And then basically the same thing in the denominator. This becomes a minus ix. And so this is where I could have done this in one step, but I felt like doing it this way. So I'm going to multiply here. I'm going to multiply the top and bottom by minus I over x. When I do this here, the x's are going to cancel, and we're going to have a minus 1 from I squared. But then the nice thing with this term, okay, we're going to have, when we multiply this over here, we're going to have x squared minus 1 over x I. And you'll notice the similarity to what we want in our goal up there. Then here, something very similar, but this is going to be a positive 1. And then this is going to be the same thing over here. So if you notice our formula over here, we want positive ones here, and I get this negative. So in order to get this to be a positive one, I'm just going to factor a minus 1 out of the whole expression and rewrite this. Okay, and you notice this is starting to look a lot like what we have up here. Okay, so I think what I want to do now is put this back into the natural log and see what we're left to do. Okay, so after all that, we've converted our formula on the left up here into this form. So here we're like really close to having the right form up, but we have, the problem is we got this minus 1 here. Well, again, we can use our logarithm rule, our properties of the logarithm. We can write this as natural log minus 1 plus, I'll distribute in this half I. Okay, so and then we'll have all this business over here. Okay, and this is looking pretty promising. Now this, but we still, let's just deal with this over here first. Now what are we doing with this natural log of -1? Well, we have a way to handle that. So let's look at this real quick. So natural log of -1, we can actually use Euler's formula. You may be familiar with this. You might be familiar with EI pi equals -1. We can actually extend this to EI pi plus 2 pi n, where n is an integer, because I guess we've got a long video, so I might as well show it really quick. But if we just focus on EI pi for a second, Euler's formula tells us this is the same thing as cosine of pi plus I sine of pi. Sine of pi is 0, cosine of pi is -1, and so that's how this works, real briefly. So what I want to do is, we found -1, we can actually express it this way. So let's actually put this back into our formula over here. So if we look at natural log of EI pi plus 2 pi n, well, this is in the exponent, so by law of properties, we can bring that out front. This will cancel, and we'll have just this I pi 2 pi n business. But the thing really to know here is there's no x term, there's no variable, this is just a number. I guess when we multiply it by half I, the i's are going to cancel and we're back to a real number. Either way, the only thing we really need to know about this is that there's no x value, so this is all just part of a constant value. And what we can do is we can just take this and have it absorbed in the constant, and we really don't have to worry about that at all. So now we're just dealing with this thing over here, and you look at it, notice that it's wholly in this format, right? It's just a different input. So instead of x, we have this whole business. So if we just kind of pattern match and go backwards, we're saying this is going to be tan inverse of x squared minus 1 over x, and we get our c1 or whatever. And so we've shown that this is the same as this, or it only differs by a constant. And so we've shown it in this direction here. So yes, that was kind of a long process to show that these are equivalent. If you've got a different way of doing that or other methods, let me know, because I find these to be pretty interesting. One thing you'll notice that I didn't mention, or I skipped over, was that we could have used the formula for inverse tanh. What I decided to do is to just skip over all that in this video and do everything kind of the long way. And what I'll do is a separate video on the inverse hyperbolic tanh and how it relates to these formulas. So look out for that. We'll do another video. I think that one's going to be shorter. Anyway, that's it. Thanks everybody. Thanks DHY. Have a good day.